Okay, last day we were talking about analysis of variance, and this is actually the third lecture relevant to analysis of variance. And the last day, remember, analysis of variance is a statistical method that allows you to compare two or more means. And last day we talked about it more from a derivative perspective. We reviewed another way of looking at analysis of variance that involved the fitting of a linear model to the data. And so we explored two slightly different kinds of models, one of which was for fixed effects. So fixed effects, remember, if the groups you're sampling or the treatments you're applying are a finite set of treatments that you are only interested in, then those effects are said to be fixed. Right? You include only the experimental treatments that you want to include and want to draw a conclusion about. The other kind of effects, the other model, random effects or random effects models, involve effects where technically you're randomly sampling from an infinite number of treatments. So you might include 10 different treatments in your study, or 10 different groups, and the conclusions you draw aren't going to be about any specific group, but it's going to be a general statement as to whether or not some of those groups differ in their mean. So that most of the calculations are entirely the same. The only differences will be something we'll talk about in today's lecture, and that is how you might complete that ANOVA. What kind of questions can you ask after an ANOVA if you reject the null hypothesis? All right, so today I'm going to go on and first I'll do another example of an ANOVA, a fairly, somewhat larger data set. And then I'll talk about some other issues associated with ANOVA, including how one might, if you reject the null hypothesis, how you might identify which means are different, and a couple of other items. So let's first go on and we'll do this analysis of variance. And so what I've done here is to actually write out a data set. So I've got the experiment here is to explore plant growth under 3 different temperatures. A company sells 3 different kinds of growth chambers, let's imagine, or 3 different kinds of heaters, and so you're only interested in plant growth at these 3 specific temperatures, at 15 degrees, at 20 degrees, and at 25 degrees. So it's a fixed effect analysis. Those are the only 3 temperatures you're interested in growing these plants at. And so you're going to grow those plants, and after some period of time, you're going to measure their heights. So that's what the data and the experiment are. So the null hypothesis is the usual one for analysis of variance, that the true mean height of plants grown at 15 equals that of those grown at 20 equals that of those grown at 25. And the alternate hypothesis can be stated as not all means are equal, or at least one of the means differs. So I normally am writing out in words the alternate hypothesis rather than using symbols. And so what I've done here is to actually tabulate the data, because there's a fair bit of it. And so all the numbers are written down here, so you can simply stop the video and just copy those down if you want to work through this example yourself. And so that's all the raw data, the data at 15 degrees, at 20 degrees, and at 25 degrees. And I've called these different groups A, B, and C in addition to giving the temperatures at which they're grown. All right, so the first step I suggest you do, and especially when you've got a lot of data like this, is to write out really summary or initial statistics that can then be used in the real heavy or number crunching involved in doing an analysis of variance. So what I'm going to do is I'm going to write down information that we're going to need. And so the first thing we need is the mean for each of these groups, because ultimately it's the means that we're interested in. And as always, if you're really doing any statistical test, you really want to have those summary statistics on hand, because the first thing you're always going to do is view your data. So we won't plot the data, but we'll certainly write some summary statistics out. So what's the mean of group A? So it ended up being 71.20. The mean for group B, x bar sub B, is 73.41, and the mean for group C equals 72.60. The sample sizes vary, so you can have different sample sizes with the single factor or one-way ANOVAs we're doing. Again, it always is more powerful to have equal sample sizes, but you can certainly carry this out with unequal. Sometimes if you're conducting an experiment, for example, you set up your experiment, you start with equal sample sizes, and some individuals die before the completion of the experiment. And so sometimes things like that happen. You can try to get around that by, maybe having a few extra individuals to include, that are included in the study, but things happen. Okay, so sample sizes vary. So group A had 10, group sample size for group B and subgroup B is 12, and then the sample size for the third group is 15. So we can have unequal sample sizes. The sample variances, so I just use the equation for the variances. And so for group A, it's 3.96. For group B, the sample variance estimate is 3.41. And for group C, the sample variance is 3.97. Now remember, there are two assumptions for the analysis of variance. One is that each of the groups that you're sampling, each of those comes from a normal distribution. And in addition to that, the variances, the true variances of the groups are the same. So it's certainly a good idea to look at the variances, and we can see these variances are all approximately in the same ballpark. They're close. They're not exactly equal, of course, but they're close. And there are ways to test, just as for a t-test, if you're doing an independent sample t-test, I've indicated you should always test whether your variances are equal using an f-test. There are tests for 3 or more variances. We won't learn those, how to calculate those by hand, but if you run an ANOVA on SAS, it will conduct one of those tests, Levine's test, which will formally test the null hypothesis that the variances are equal. So when you run an ANOVA on SAS, you'll see that output, and you should look at it, because if you violate that assumption, you might need to transform your data. So remember, I talked about transformations. Or if beyond this course, you might need to do a non-parametric analog, that is, give up on doing an ANOVA and use one of those tests, a non-parametric test that we won't cover in this course, that has fewer assumptions embedded in it. Anyway, let me continue writing down summary statistics. So I've got the mean, sample size, the variance of each of the samples, and I'm going to write down some intermediate calculations that will be useful when we do the number crunching for the ANOVA. So what I'm going to write here is the sum of the x's for group 1, the sum of the x's squared for group 1. And so if I square all the values, all 10 values for group A, and sum them, this ends up equaling 50,734. For group B, the sum of the x's squared is 64,721, and for group C, the sum of the x's squared was 79121. We also need the sum of the x's. In fact, we already have kind of calculated it because we got the mean. So the sum of the values for this group was 712. The sum of the values for group B was 881. And the sum of the values for group C is 1089. So I would recommend that when you're doing ANOVA, you do it in this organized way. That is, you begin with, obviously, your data set. You have the raw data. You then move to computing, in an organized way, these different intermediate and summary statistics. Because it'll be easier to check, because there's lots of calculations, it'll be easier to check on things if you've made a mistake, if you always do it in the same organized fashion. Okay, so those are the initial summary statistics. And now, if you recall, there's a few quantities we might want to use in our calculations of sums of squares. So one thing we want is the double sum of the xij's. So that's the sum of all possible values. So it's kind of easy for me to get that because it's just, I have already these intermediate sums, the sums for each group. So I'm just going to add those together. So that ends up equaling 2682. I also want the double sum of every observation squared. So that's also easy because I have the sum of the squared observations from each of the groups. I'm just going to add those three things together. And if I do that, I get a large number, 194,576. And finally, we also want the total sample size, big N, and so it's equal to the sum of the sample sizes. Pretty trivial. And that ends up equaling 37. Okay, so that's the initial summary statistics and intermediate calculations that will be helpful in then computing sums of squares. So let's do that. Let's now move on and calculate the sums of squares. So I'll move to the next page. And so remember, we need to calculate the total sum of squares. And it equals the double sum of the xij squared, which is something we just calculated, minus the sum of the xij, so the sum of all values, squared, divided by big N. So we've already got all that stuff. And so this on the previous page. So the total sum of squares equals 194,576 minus 2682 squared over 37. And so that ended up equaling 167.25. So that's the total. Then we need what I earlier called the group sum of squares. Could be called the treatment sum of squares. You could call it the temperature sum of squares. In other words, you're giving it an informative title that tells someone that you're comparing things, groups that are different, were grown at different temperatures. Anyway, I'll just call it the group sum of squares for now. And so it equals, or the equation you might remember, is the sum from I equals 1 to k of this sum from j equals 1 to ni of the xij's, which you then square and divide by their associated sample size. So that's like the first term, minus this thing again, the double sum of the xij's, all squared, over big N. All right, as I said, this is the one that it looks a little difficult, but it isn't. So this first term here, it just says, take the sum of each of the groups, square it, and divide it by its sample size. So this is simply 712 squared over 10 plus 881 squared over 12 plus 1089 squared over 15 minus this quantity, which we've kind of already written down, right? It's 2682 squared over 37. And if you calculate that out, the group sum of squares equals 27.13. So we need one more sum of squares, and that is the error, or sometimes called the residual. So the error, or the within sum of squares, it has all those names depending on which book you look at and which day of the week it is. So the error sum of squares is given by the double sum of the xij's squared minus the sum from I equals 1 to k of the sum from j equals 1 to ni of the xij's. So you're summing those, squaring, and divided by their sample sizes. So that's a term we've already calculated above. And so the error sum of squares equals the sum of the x's squared, which is 194,576, minus this thing again, 712 squared over 10 plus 881 squared over 12 plus 1089 squared over 15. And so if you crunch that out, you should have gotten, well, I claim I get 140.12. So that's really the heaviest number crunching. But if you need to really do a bunch of these, because you need practice in sorting it all out. Sure, they're just equations, and I know all of you can really read an equation and probably use it. But you really need to go through the mechanics of doing these, or you'll foul it up, because there's lots of calculations to do. So make sure you do a number of these examples, and there are examples, I think, in problem set 7, and there are a number in the book, and you can work through the examples that I've given you as well. It probably would be a good idea. Okay, so we're not done yet, right? So now we've got the sums of squares. And so now what we can do is we can go straight to constructing our ANOVA table. Remember, you're always going to end an ANOVA and present the results of an ANOVA in an ANOVA table. So here's my ANOVA table. You can call it something if you want to. Plant growth versus temperature, or different temperatures. And so an ANOVA has headings such as source of variation, I'll just call it source, degrees of freedom, sum of squares, so I'll just put SS down, mean square, and then the test statistic, the F-calc value. So those are the headings. Sources of variation, total. Group or treatment or temperature, whatever you happen to call the variable that you're using to group things. Really, it's a classifying variable. And then we have the error or residual source. So degrees of freedom, total is big N minus 1. So we had, this is 36 because there were a total of 37 observations. The group, remember, is K minus 1. K is the number of groups, minus 1. So we had 3 groups, right? Plants grown at 3 different temperatures. So 2 degrees of freedom. And the error is big N minus K. So that's 37 minus 3 is 34. And remember that, right, the group plus error should add up to the total degrees of freedom. It should add up to N minus 1, which it does. Now let's write in the sums of squares. So remember, we calculated sums of squares on the previous page. So I'm just going to enter those directly into this table. So total sum of squares was 167.25. The group sum of squares was 27.13. And the error sum of squares was 140.12. Check that these two things add up to the total, right? So that's a double check. There's lots of calculations here. Make sure that the group and error sum of squares add up to the total. If they don't, you've made a mistake. So if you've done things in a systematic way, you can go back and check over where you might have blown the calculations. Okay, so now things are kind of easy, right? We can just complete the analysis right in the table. So to get the mean square for group, you just divide the sum of squares for groups by its associated degrees of freedom. So 27.13 divided by 2, and that's 13.56. Likewise for the error sum of squares, so error mean square for error, it's 140.12 divided by 34. This is 4.12. And now the F calculation is really simple. You're always dividing the group mean square by the error mean square. And if you do that, you get a value of 3.29. Okay, so now we've got our test statistic, and we need to ask the question, is this an unusually large value? If indeed it is true that there is no difference in the growth of plants, they have the same means, is this an unusually large number? And so we need to refer to the critical values of the F distribution. So critical values of F, degrees of freedom, there were 2 degrees of freedom associated with the denominator. with the numerator, right, the group degrees of freedom. Group is always in the numerator, so 2 degrees of freedom in the numerator, 34 degrees of freedom in the denominator, always looking up at alpha 1 equal 0.05, so make sure you look at the right F tables. And if you do this, it's 3.28, so our F calc is just slightly larger than the critical value, so we reject the null hypothesis. Conclude that one or more of the means differ. And we don't know which mean differs, right? So for an ANOVA, this is as far as we can go at this point. If you reject the null hypothesis, at least one of those means differs from the others. And just to sketch out again the F distribution for 2 and 34 degrees of freedom, it kind of looks like this. This is 0 over here. This is the F distribution. Right, you're setting up a rejection region with all alpha equal 0.05 sitting under this portion of the curve. Here's the critical value, 3.28. F, our test statistic, 3.29, just falls inside the rejection region. So we reject the null hypothesis. Now, if you were really doing this experiment and it was important, you might be a bit concerned, even though you formally, we're using this hard and fast criterion, right? If you're greater than the critical value rejecting, you might want to do this experiment again or increase the sample size to ensure that, in fact, you're drawing the correct conclusion, right? Sometimes you can get unlucky. It could well be, right, because you have sampling effects, you're random sampling. So it could well be that there is no difference and you got unlucky, right? There's a 5% chance you're going to draw the wrong conclusion. Why? Because we're always using alpha equal 0.05. Okay, so that's the conclusion thus far from this analysis of variance. Now let me just go on and talk about one other statistic that people often use when they conduct an analysis of variance. And in fact, if you do an ANOVA on SAS, you'll see reported something called the R-squared value, which is sometimes also called the coefficient of determination. It's used for a number of different statistics. And so R-squared it's a descriptive measure, and it describes how much variation is explained. So it describes the amount of variation explained by groups. The fact that I've got these things in groups that were grown at different temperatures, that's an explanatory variable. If you go back to, remember we talked about response variables. The response variable, remember here, is going to be plant growth or plant height. We're trying to explain plant height as a function of the temperature at which they're grown. So R squared is an estimate of how much variation you are explaining. And so from an ANOVA, R squared equals the sum of squares for groups divided by the total sum of squares, SS total. Or I guess I was writing it the other way, it doesn't matter. Group sum of squares, sorry, sometimes flip-flop the way in which I write these, versus total over total sum of squares. Those are the same things, all right? I just wrote the sum of squares differently. And so in this case, it's R squared equals 27.13 divided by the total, which was 167.25. So R squared equals 0.16. Or sometimes this is expressed as a percentage. So as a percent, R squared is 16%. Or in this experiment, 16% of the variation in plant height is explained by growth temperature. So 16% of the variation in plant height is explained by the temperature in which you grow them. Right, so it's a useful adjunct. We've rejected the null hypothesis. We know one or more of those means differ, so it would seem that the growth temperature is doing something. How much variation in height does temperature explain? It explains 16%. So it's a useful adjunct. And you know what that value it's not a super high percentage. You might be happier if you had explained 80%, but you're explaining some portion of the variation. So often someone might say, and it depends on really what you want to do, what's biologically meaningful to you in the experiment you're conducting. This may be satisfactory, or maybe it isn't. Maybe you want to, if you really want to grow plants larger, temperature at growing them, 15, 20, 25, is not really altering their growth very much. If you really need to grow them different heights, you might try, something else. Try some different temperatures. Try some fertilizer. Try higher light levels, right? If that was your purpose, to grow bigger plants, while there really are differences in growth as a function of temperature, this percent of variation explained may not be satisfactory to you, even though you have an effect. So that's an issue for the experimenter to deal with. Formally, we've concluded there are differences in growth, but from a practical sense, that may or may not be satisfactory for the particular experimenter, depending on their purposes. Okay, let's move on. So let's leave this experiment for now and talk about how to find out. Remember, after ANOVA, if you reject the null hypothesis, it means that at least one mean differs. So one or more means differ. But you don't know. It doesn't tell you which one, which means. So there, I'll talk about now is how you can find that out. So first I'll talk about things called a priori or planned comparisons. So you can use the word a priori or planned. And so I won't spend much time on these. These probably should be carried out more often than they are, but you can read about them in more detail if you want to once you're out of this course. So a priori comparisons are comparisons that are planned, that were planned at the time the experiment was conducted. Okay, so embedded in some experiment. I'll try to make up an example. Let's imagine you were growing algae and you wanted to look at the cell size of algae, and you grew them in different pHs. But some of them also, the media you're growing them in differ. So you grow them in different pHs, and you're also provided a carbon source. So you might have some growing at pH, 3, pH 4, pH 5, pH 6, pH 7. You can grow them for some period of time. But also, you had some other sugars in here. So these might have been glucose, and this can be fructose. Now let's make it sucrose. These are 2 carbon sugars. They have 2 ring sugars. Sucrose. So that's the experiment. Do algae grow to different sizes in these different media? So you put a bunch of algae in, you grow them for some period of time, you measure them. But embedded in this experiment, you also want to do another comparison where you're comparing glucose, if you like, the mean glucose growth to that of sucrose. Okay, so you're going to first do an ANOVA. As before, you've got 5 treatments or 5 groups you're comparing. You can do that. But then you might want to compare the glucose-grown ones to the fructose-grown. And that was part of the experimental design at the outset. I mean, this is kind of a stupid experimental design, but let's not worry about that. It's stupid because why are you growing ones? You've got 2 different strange things happening. You've got the lowest pHs are growing with glucose, and the higher ones are growing at with sucrose, and it doesn't really make any sense experimentally. But let's not worry about that. Okay, so let's imagine that was part of the plan, to compare the one ring sugar glucose versus the two ring sugars sucrose growth. And so to do that, you effectively do a modified form of a t-test. And so it's going to be, what you need is to get the standard error, and that's given by the square root of, get the error mean square. So I'm going to go back, I would look at my ANOVA table and pull out the error mean square right out of the ANOVA table and multiply it by 1 over whatever the first mean sample size is, 1 over n1, plus whatever the sample size for the second mean is. So in my example here, however many algae there were in these 2 things, that's going to be the sample size, so the sum of the sample sizes for those. N2 might be this group over here, whatever the sample size for that was. This just comes straight out of the table. Take the square root of it, so now I've got the standard error. And the t calculation is simply going to be the difference in means, so the mean for the guys grown at pH, well, it's at glucose, the mean of the guys for glucose minus the mean of the guys grown in sucrose. Right, so calculate those means and divide it by the standard error. So a straight ahead t-test, the only differences being the standard error is constructed by taking the error mean square out of the ANOVA table, multiply it by the appropriate sample sizes, it can 1 over the reciprocal of the sample sizes, calculate t, and then you need to look up the t critical value with n minus k degrees of freedom. Right? It's the degrees of freedom associated with the mean square for error. And this can in principle be a 1 or 2-sided test. So look up alpha equals 0.5, alpha 1 or alpha 2, depending on what if you had some a priori notion as to which way they might differ. Okay, so this is a priori comparison. It has to be part of the experimental design at the outset. Embedded in the study, and the plan for this experiment is, I'm going to compare some number of sample means, and more explicitly, I want to compare these 2 or these 2 groups also. And you can only do a small number of these comparisons. Right? Within the context of a particular ANOVA or analysis. So there's a formal way of knowing how many such comparisons you can do and which ones you can do. There were restrictions on if you're doing more. Let's say I'm comparing glucose and sucrose, and then somehow I want to compare, for example, pH 6 with pH 4. It might be possible to do those as a separate a priori comparison as well, but there are some things that need to be checked on, some calculations that need to be done to ensure that you can do that comparison. So I won't go elaborate on how many and which comparisons you can do. That's left for beyond this course, but you can read up. It's not that challenging to do. There are other texts that might deal with that. So we're not going to deal with that for this course. For the purposes of this course, a priori comparisons are comparisons you can do if you reject the null hypothesis for ANOVA, and part of the experimental plan or design was to compare a tiny handful of means. So in this case, just one other comparison. And so the calculation is pretty simple. It's really a t calculation. You need to get the standard error as shown here. And then you do this t calculation. You subtract the means you're comparing, divide by the standard error, and look up the critical values with n minus k degrees of freedom in the t tables. So those are for planned comparisons. Perhaps more often people do unplanned comparisons. And both of these, incidentally, a priori comparisons and the unplanned, really only apply to fixed effect ANOVA. So if you have fixed effects, you reject the null hypothesis, you can go ahead and do an a priori test if it's part of your experimental design, or you can do a set of unplanned comparisons. And there are a bunch of slightly different unplanned comparison tests you can do that vary in power. And we're going to do one called the Tukey-Kramer test, but I'll do that in the next lecture.